A 7,500-ton hotel, not demolished, not rebuilt, moved, rolled whole through Sanya, China, on 254 axle lines, rotated 63 degrees clockwise, then 63 degrees back. One imbalance, one miscalculation, and the structure tears itself apart. This is extreme engineering at a scale that looks impossible even after it succeeds. The question is, how does a whole building move without tipping over? Standard heavy cargo is highly predictable. A steel generator or a compact pressure vessel has clear load paths and a centralized center of gravity. A complete building is entirely different. It is a massive, hollow shell of asymmetrical walls, uneven floor weights, and sweeping empty spaces. Concrete and masonry structures are engineered to stand stationary on a solid foundation, not to flex, bend, or ride over uneven terrain. When lifted, the weight does not distribute evenly. Instead, it concentrates heavily on specific structural columns, sending immense stress through areas never designed to hold it. This shifts the center of gravity dangerously high or off-center. If the support points yield even slightly, the center of pressure migrates. Structural failure, ground collapse, or transporter failure can trigger a catastrophic collapse long before the first degree of visible tilt is ever registered. Total weight is only a fraction of the challenge. The true battle is managing structural vulnerability under dynamic loads. There is absolutely no margin for error. How do engineers move these fragile giants without tipping them over? The solution to this mechanical puzzle is the self-propelled modular transporter, or SPMT. Historically, heavy relocations relied on steel rollers, jacking systems, or partial demolition. That changed in the 1970s with early hydraulic trailers, which evolved by the 1980s into the first purpose-built SPMTs. Developed by pioneers like Schuylerle, Goldhofer, Cometto, and Mamoet, this technology replaced rigid platforms with an adaptable building block approach. An SPMT platform is a combined network of linked axle lines, where an axle line is simply a row of independently supported wheels. Because these modules are fully interchangeable, engineers link them longitudinally, laterally, or in custom layouts to match the exact shape of a building. Adding axle lines increases vertical support, distributing the massive load across a wider footprint to protect the ground below. The complex hydraulic and electronic networks remain completely hidden beneath the simple frame. A diesel-powered power pack unit, or PPU, supplies hydraulic pressure and electrical energy through this concealed network. This fluid drives the propulsion, braking, and vertical elevation of each axle, allowing up to 60 centimeters of height adjustment. With each wheel set capable of swiveling up to 360 degrees, the platform executes complex steering maneuvers. It can travel forward, sideways, diagonally, or spin in a tight carousel turn. By adjusting the height and steering angle of each individual wheel row, the platform turns an unstable building into a highly maneuverable load. On February 21, 2023, in Sanya, Hainan Province, China, engineers put these capabilities to an extreme test. The target of the operation associated with the Hongtang Bay Hotel development was a massive structure weighing an estimated 7,500 tons. While some trade reports identify the load as the completed hotel building itself, specialized engineering records suggest the transport was actually a fabricated steel base designed to support the future resort. To shoulder this asymmetric mass, transport contractors Sinotrans Heavy Lift and Vastwind Engineering Logistics assembled an immense custom fan-shaped layout of Schuylerle SPMT units. Trade journals record the deployment of 254 axle lines powered by 15 individual power pack units, though alternative project logs cite a configuration of 244 axle lines and 13 power packs. The team aimed to move this colossal platform over a 500-meter corridor, a feat the contractors claimed as the heaviest building transport on wheels. The true challenge lay in navigating the tight transport corridor. The massive footprint did not align with the narrow path, requiring a highly complex maneuvering sequence. Using the synchronized 360-degree steering of the wheels, operators executed a precise 63-degree clockwise carousel rotation to clear local obstacles, followed by an equal counterclockwise rotation to realign the structure with its new foundation pads. Over an 8-hour shift, the entire 7,500-ton platform rolled, pivoted, and settled onto its new foundations. The sheer scale of this move raised a fundamental question. When dealing with thousands of tons of unevenly distributed weight on a rotating platform, How do engineers prevent the tiny mechanical errors that lead to catastrophic structural failure? This modular mobility solves logistical bottlenecks across heavy industry. In shipyards, operators move offshore platform topsides, the large upper sections containing processing equipment, to align them with transport vessels. For energy infrastructure, contractors assemble multi-thousand-ton refinery modules inside controlled off-site facilities to bypass congested plant sites before rolling them into place. Prefabricated industrial buildings are built miles from their final destinations to avoid hazardous local terrain. While SPMTs conquer these open routes on wheels, dense urban environments like the Shanghai Shikumen block mark the boundary, requiring slow hydraulic walking robots rather than wheeled modular transporters. Without perfect control, a multi-thousand-ton structure becomes an active hazard. The entire operation rests on a knife edge of physics. If the center of gravity shifts even slightly outside the support footprint, gravity turns the building into a massive lever, initiating a catastrophic tipping moment. Underneath, a single soft patch of soil can trigger localized settlement. When one side drops, weight concentrates, overloading individual axle lines beyond their braking strength. As the platform turns, different wheels trace unequal paths, generating massive lateral forces that try to rip the transport frame apart. Torsion builds invisibly, one corner of the foundation rotates while another resists, sending shearing stresses through concrete walls. Even under calm skies, wind gusts, braking, and road bumps add unpredictable dynamic forces. A structure can appear perfectly level right up to the moment its internal load paths fracture. The ground is part of the machine. Every fraction of a second, sensors underneath the platform gather data. Load cells monitor the exact force pressing down on each support point. Inclinometers track microscopic changes in tilt, and stroke gauges measure the precise position of hydraulic cylinders. This stream of measurements feeds directly into a central controller, which compares the live state of the platform with its target. It is a continuous closed loop. Sense, calculate, adjust, and measure again, repeating 10 times every second. When the platform turns, different wheel sets trace separate paths. The computer coordinates these varying angles, directing hundreds of wheels to move as one unit. Simultaneously, the hydraulic suspension under each axle shifts pressure and height. This adjustment protects the internal load paths of the building, preventing structural shearing that tears masonry apart. Power pack outputs are synchronized across the entire assembly. If a system faults, redundant power and automated braking isolate the issue to bring the platform to a controlled stop. The computer provides the calculation, but a human operator remains the sole authority behind every movement. Before a single wheel turns, structural engineer Dr. Liwei calculates the building's center of gravity and designs internal steel bracing to establish secure load support points. Geotechnical engineer Zhang Ming then analyzes soil core samples and maps underground utilities along the Sanya route. These inputs build a digital route model, revealing exactly where native road surfaces and bridge decks will fail under a concentrated footprint of 150 kilopascals. To prevent ground collapse, crews lay 12mm high-strength steel plates over timber sleepers and bolt auxiliary steel beams to the pedestrian bridge structure. After weeks of simulation rehearsals and securing municipal superload permits, Transport Superintendent Chen Hao initiates the night move under total traffic shutdowns. As the platform slowly rolls, the team continuously monitors live soil settlement, structural alignment, and real-time column strain. Today, the line between permanent architecture and mobile cargo has vanished. As cities grow, we no longer demolish our past, we relocate it. The true triumph is not raw power, but the microscopic control keeping these giants standing. What should we move next? Share your thoughts below.